Test review is for Daniel, who's still out on quarantine. Hope you're having a good fall break. For Tom, I hope you're doing better. And for Emma, who had a nice trip to the mountains. So do your best to get this done before you come back on a week from Monday. So it would be helpful to have your book with you. I hope you brought your book home, Emma. So on problem 1, we're looking at page 148, 10 and 13, and just really easy. What are the dimensions of the first one from problem 10, which is 2 rows by 4 columns, and problem 13 is 2 rows by 3 columns. And then problem 2 is page 148, number 15 and 16 out of the B matrix. What's B21, which means row 2, column 1, which is 7. And what's B32, which is row 3, column 2, which is 12. And then this one is one that we had done for the quiz, I believe. If we have an A 2x2 matrix, a B 2x3, and a C 3x3, what are the dimensions of the matrix multiplied? So A times B would be a 2x2 times the 2x3, and notice I have circled the inner 2's, which have to match for a multiply to take place. So the dimensions of the final multiplication product are the outer dimensions, or 2 by 3. Now, if I try to multiply A times C, I have a 2 by 2 times a 3 by 3, and the inner dimensions, 2 and 3, don't match, so that's undefined. It can't be done. But if I try to multiply B and C, then I have a 2 by 3 times a 3 by 3, and the inner dimension 3 matches. So I have the outer dimensions, again, 2 by 3. But if I try to multiply B times A, I have a 2 by 3 times a 2 by 2, and the inner dimensions 3 and 2 don't match, so that's undefined. Now, if I have a simple matrix multiply of 3 times the matrix 4025 minus 2 times the matrix 2413, the first matrix would multiply out to 120615. And the second one would be minus 4826. So subtracting elements, I have 12 minus 4 is 8, 0 minus 8 is negative 8, 6 minus 2 is 4, and 15 minus 6 is 9 for my answer, 8, negative 8, 4, 9. Now for 5, I want to take the set of two equations, 2x plus y equals 8, and 3x plus 2y equals 13, giving me a matrix 2, 1, 3, 2 times xy equals 8, 13. Now this is a nice easy one to take an inverse of. So to take an inverse, I take the determinant first, which is 2 times 2 minus 3 times 1, or 4 minus 3 is 1. And the inverse is 1 over the determinant, which is 1. And then I interchange the 2 and 2 on the main diagonal, which leaves them the same, and put negatives on the 1 and the 3. So my inverse is 2, negative 1, negative 3, 2. And if I multiply that by my B matrix, 8, 13, I will get my x, my answer, which is 2 times 8 is 16, minus 3 is 3 for x, and negative 3 times 8, negative 24, plus 2 times 13, 26, negative 24 plus 26 is 2 for y. So my answer is 3, 2, the column vector. And for 6, we want to find the value of A for which the inverse is undefined. The inverse is undefined if the determinant is 0 because it's 1 over determinant for the inverse. So here I have 8 times 2, 16 minus a squared. I set that to 0. And I get 16 equals a squared, or a is the square root of 16, which is plus or minus 4. So when a determinant of a is 0, a inverse is 1 over a, which makes it undefined. So negative 4 and positive 4 are my answers. Now on page 149, you'd have to look at the bar chart to get the matrix. But we're just reading the bar chart off the top of page 149. So the C 3 by 4 matrix is the 1, 2, 1, 2 for the year 2011, 2, 3, 2, 1 for the year 2012, and 4, 4, 1, 2 for the year 2013. Now the rows correspond to years and the columns correspond to students, which I haven't listed there. But C23, row 2, column 3 is 2, and that corresponds to Valerie in the year 2012. Okay, 8 is a real simple one. Find A and B for 4 times the column vector A3 minus 2 times the column vector 6B. So that gives me 4A minus 12 on the top row, which is 4A equals 12 or A equals 3, and 12 minus 2B or 12 equals 2B or B equals 6 for the bottom row. Now 10 is the extra credit, so we're taking the A matrix 1, 2, negative 1, 1, negative 4, 1, and 2, 2, 1, and as we're showing, replicating the first row becomes the first column becomes the fourth column outside, so we can do the determinant, and the second column becomes the fifth column. Now the A sub x determinant is putting in the B matrix in for the first column, negative 1, 2, 6, and we put in, this is on page 169, and it's the same matrix as I show for problem 9. So on this one, I'm going to replicate the first column as the fourth column and the second column as the fifth column. Now to take the determinant for A, I take on my diagonal 1 times negative 4 times 1, negative 4, plus 2 times 1 times 2, 4, plus negative 1 times 1 times 2, negative 2. And then I minus the 2 times negative 4 times negative 1, 8, plus 2 times 1 times 1, 2, plus 1 times 1 times 1, 2. And that gives me negative 2 minus 12 is negative 14. Now on the A sub x determinant, I take negative 1 times negative 4 times 1 is 4, 2 times 1 times 6 is 12, and negative 1 times 2 times 2 is negative 4. Minus, going back up the other way, 6 times negative 4 times negative 1 are 24, 2 times 1 times negative 1 minus 2, 1 times 2 times 2, 4. So that gives me 12 minus 26 is negative 14. So x is equal to the determinant of A sub x over the determinant of A, or negative 14 over negative 14 equals 1. So this will be the extra credit one if you have to do it just for x. So you just have to take A sub determinant of A sub x over determinant of A. And the problem it was taken from is on page 169, example 4, which is the x plus 2y minus c equals negative 1, and x minus 4y plus c equals 2, and 2x plus 2y plus c equals 6, giving me the A matrix, which we just used above, 1, 2, negative 1, 1, 4, one, negative 4, 1, and 2, 2, 1 times x, y, z column vector equals the B matrix, which we used in the A sub x first column, negative 1, 2, 6. And then problem 11 is to take and solve the problem 3 times x, the x column vector, is minus 2, 6, negative 23, 13 equals 4, 6, minus 7, 1. So I'm going to add the 2, 6, negative 23, 13 matrix over like it were a number over to the other side. So I'll have now adding up elements. 4 and 2 is 6 for my first row 1, column 1. 6 plus 6 is 12 for my row 1, column 2. Negative 7 minus 23 is negative 30 for my row 2, column 1. And 1 minus 13 is negative 12 for my row 2, column 2. But that's equal to 3x because 3x is what we started with on the left. So I have to divide every element in the matrix by 3. And that gives me 6 divided by 3 or 2, 12 divided by 3 or 4, negative 30 divided by 3 or negative 10, and negative 12 divided by 3 or negative 4. And for 12, we have the A matrix 3, 2, 2, 1 times x plus the column vector 3, 2 equals the column vector 2, 6. So before I can do anything else, I have to subtract the column vector 3, 2 over and subtracted from 2, 6. So 2 minus 3 is negative 1, and 6 minus 2 is 4. So now I have the matrix 3, 2, 2, 1 times x equals negative 1, 4. Now, in order to do the inverse, I have to do the determinant, which is 3 times 1 minus 2 times 2. 3 minus 4 is negative 1. And the inverse is 1 over the determinant, 1 over negative 1. And I interchange the main diagonal elements, 3 and 1, so it becomes 1 and 3. And I put negative 2 on negatives on the 2's. So now I multiply that all by negative 1, and I get an inverse of negative 1, 2, 2, negative 3. And then to get my x vector, I get A inverse, which I just did, times B, which was negative 1, 4. And so now I can multiply negative 1, 2, 2, negative 3 times negative 1, 4. And multiplying that, I get negative 1 times negative 1 is 1, plus 2 times 4 is 8, or 1 plus 8 is 9. And 2 times negative 1 plus negative 3 times 4 is negative 2 minus 12 is negative 14. So my x column vector, my answer is 9, negative 14. And for problem 13, we have 4x plus 3y equals 8, 6x minus y equals 1, giving us the A matrix of 4, 3, 6 minus 1 times xy equals 8, 1. So the determinant of A is 4 times negative 1 minus 6 times 3, or negative 4 minus 18 is negative 22. The determinant for A sub x is placing 8, 1 in the first column. So we have 8 times negative 1 minus 3 times 1. Negative 8 minus 3 is negative 11. The determinant for A sub y is placing the B matrix 8, 1 in the second column. So we have for that determinant 4 minus 1, 4 minus 6 minus 8. 4 minus 48 is negative 44. And x is equal to the determinant of A sub x over the determinant of A, negative 11 over negative 22, or 1/2. And y is equal to the determinant of A sub y over the determinant of A, negative 44 over negative 22, which is 2. So my xy answer is 1/2, comma 2. Now, this is just showing what happens in the last section. Translation is performed by matrix addition. Reflection and rotation is performed by matrix multiplication. And dilation is performed by scalar multiplication. Now, the next one is, which of the following is always true for an n by n matrix? Well, the distributive rule, A times B plus C, since they're all n by n and work, is equal to A times B plus A times C always works. But A times B equals B times A is not always true, because the order that I multiply in makes quite a difference. But A plus B equals B plus A is commutative, and that works since they're both n by n. But AB squared is not equal to A squared times B squared, because, again, the order that I multiply in make a difference. So A and C are the true ones there. Now, given that A n by n, such that the determinant A is not 0, which of the following are true? Well, A has a multiplicative inverse, that's true. A n by n times x n by 1 equals B n by 1, that's our normal setup, is always solvable because I can always find an inverse, so that's true. And if AB equals AC, then B equals C, which is true. So all of those are true. Now this one is about translation. So on page 177, number 5, we have 3 points. The point A, which is 1, 3, the point B, which is 2, 1, and the point C, which is 3, 5, which is plotted on the graph on the right side. And then we're going to translate 5 to the left. So the translation is by matrix addition, as we said earlier. So that's negative 5's on the top row and 0, leaving the bottom row unchanged, giving us negative 4, negative 3, negative 2, 3, 1, 5. And that's plotted in the triangle to the left, which, as you can see, is just all left shifted by 5. Now, problem 18 is taking the area of a triangle which has points on page 165, example 5, has points -3, 1, 0.13, and 0.21. And to get the area of the triangle, we take half the absolute value with the third row as 1, 1, 1. So again, we replicate the first column as the fourth column, and the second column as the fifth column. And for the area, now we take 1/2 the absolute value of the determinant, which is -3 times 3 times 1, or -9, 1 times 1 times 1, or 1, 2 times 1 times 1, or 2, minus, coming up now, 1 times 3 times 2, 6, plus 1 times 1 times -3, -3, plus 1 times 1 times 1. So 1/2 the absolute value of -6 minus 4, or 1/2 the absolute value of -10, which is 5 square units. Now on 19, we have a dilation, page 117, number 17, and the points K, J, L, as K is 0, 2, J is 1, 1, and L is 1, 3, is shown the bottom triangle. And if we multiply everything by 2, that's making it twice as far away each point from the origin. So J prime, K prime, and L prime are 0, 4, 2, 2, and 6, 2, which are shown graphed above. And the last problem, page 178, number 15, is rotate the points H, G, I by 270 degrees. And on 2 pages preceding, it shows the matrix for the 270-degree rotation as 0, 1, -1, 0. And if I multiply that by the point H, which is 1, 2, the point G, which is 1, 1, and the point I, which is 4, 2, which is shown as the triangle in quadrant 1, then when I multiply that, I get the bottom row for HGI becomes the top row, the y's interchange with the x's. And when I multiply the -1 through, it gives me the negative of the top row of the HGI, so the y's become the negative x's. So this turns into 2, -1, 1, -1, 2, -4, which is shown as the triangle in the quadrant 4. And as you can see, it's been rotated by 270 degrees. So do your best now to get this in by a week from Monday. You have plenty of time to do it, and you can do it whenever it suits you. But don't put this off by the time we get back so that we can be caught up. So thank you very much. Enjoy your fall break. I intend to. I'll be done now.